Hey, how's it going everyone? Welcome to this video on chapter 13.5. Today we're going to have a look at curve sketching. So we're looking at points where a differential function is neither increasing or decreasing. So such that the function is stationary and its gradient is zero. And we had a look at that roughly, rough little sketch here, last video where we're looking at points along the graph and what the tangent does at each of those. So for example, these points here, if we drew tangents all along there, it's increasing. The gradient of the tangents are increasing, whereas over here we'll have negative gradients, so they're decreasing. What we're looking at today is these particular points here and here, where they're basically horizontal. So they're neither increasing or decreasing, and that's because they're the turning points, essentially. So identifying these stationary points, SPs, it provides information which can assist us in curve sketching or sketching the curve. Just to start with, we've got stationary points. So stationary points on a curve y equals f of x. Well, the stationary points occur when the gradient f dash of x is equal to 0. And there's three types of stationary points. We can say a local minimum and a local maximum. We've also got a third option of a stationary point of inflection. So that's when we're looking at cubics. If you remember, stationary point of inflection is where it goes concave up to concave down or concave down to concave up. So it's that little spot there. The word local means that the point is minimum or maximum in a particular locality or neighborhood. So we might have lots of different turning points or maximum turning points. This one here has a local maximum relevant to its neighbors of its points there, whereas over here we've got other maximum points. So we say a local minimum or maximum when there's more than one point. To determine the nature of a stationary point, so for each of the three types of stationary points, we said f dash of x is going to equal 0. So this means that the tangents to the curve at these points are horizontal. Examining the slope of the tangent to the curve immediately before and immediately after the stationary point, the nature of the type of stationary point can be determined. So essentially what it's saying is, if we have on the graph looks like a local minimum, well, we can investigate the nature of it by looking at the slopes of the tangent immediately before and after. So let's say that occurs at x equals 1. Well, I can have a look at the point x equals 0 and one above it, which x equals 2. So I say I can develop what's called a nature table. So the stationary point, what is it? Well, we look at the slope. Um, Immediately before and after, so at 0 and 2. And so what happens at the slope? Well, we've got a decreasing gradient. So the slope at 0 is decreasing. At 1, it's a horizontal. At 2, it's increasing. So it looks like the stationary point is going to be a minimum. We can also have a look at the sign diagrams. So we've got positive and negative. Well, what happens before? Well, our gradient is in the negatives at the point is our turning point, and it changes to positive. So that would be our sign diagram for a local minimum. A similar case for a maximum. So same example, we'll say 1 and 0 and 2. So at 0, 1 and 2, we've got the slope of the tangent. So at 0, somewhere over here, it's going to be a increasing gradient. At 1, we've got a horizontal, and at 2, it looks like we've got a decreasing. So therefore, we have a local maximum. And again, the sign diagram, we've got positive and negative. Well, it looks like our slope's starting at the positive. At the turning point, it changes and now into the negatives. The third option is when we have a stationary point of inflection. So that's when it looks like one of those or one of those. And same thing, we'll take 1, 0, and the point 2. Well, the slope immediately before it is increasing. At 1, it's horizontal, and then at 2, again, we're increasing. So it's going to look like that. And then the sign diagram, we've got positive and negative. Okay, we're starting at the positives. We get to the turning point, and then we end up going back into the positives. So it looks something like that. So we can identify stationary points and their nature by establishing where our derivative f of x is equal to 0. So if we had our original function y equals x squared, our derivative, or dy dx in this case, would be 2x, and we establish where it is 0, so I'd say 2x equals 0. Well, that happens at x equals 0. Okay, and as a diagram, that's what x squared looks like. We've got a turning point through the origin, which is the x equals 0 coordinate, which we just worked out there. Okay, just as a quick little example for that first point. The second part is determine the nature by drawing the sign diagram. Of f dash of x around the stationary point, or alternatively by testing the slope of the tangent at selected points either side of, as I showed before. Or test Alright, so two options there: establish where that equals zeros, or determine the sign diagram, or test using the left and right method. So we'll have a look at an example. Determine the stationary points of f of x is 2 plus 4x take 2x squared take x cubed, and justify their nature. So first thing, find out what f dash of x is. So we'll have a 4 take 4x take 3x squared. So the stationary points occur when f dash of x is equal to 0. So I say 4 take 4x take 3x squared is equal to 0. If I solve that, so I've got a quadratic here, factorize that. So say either x equals 2 on 3, or x equals minus 2. It's a 2. And so I say when x is 2/3, my f of x or f of 2/3 is going to be 2 plus 4 and solving that I get 94 over 27, and then at x equals minus 2, I get minus 6. So the stationary points are going to be at 2/3, 94 over 27, and minus 2, minus 6. So because we know f dash of x is 2 take 3x 2 plus x, I can make a sign diagram using that information. So we've got plus and minus. All my zeros are going to be at minus 2 and 2/3. I've got a negative x over here, so I'm going to start in the negatives. At minus 2, here's my 0. I go across. So in this case, we've got a that kind of shape for at minus 2, which if we go back to this slide here, it's exactly the same as that one there, which means we've got a local minimum. And then the opposite for this one, so that means we've got a local max. So at x equals minus 2, the gradient changes from negative to positive. So it changes from negative to positive. So minus 2, 6 is going to be a minimum turning point. the other one we start from positive and we go to negative, meaning that it's a maximum. Part B, the curve y equals ax squared plus bx, take 24, has a stationary point at -1, -25. Calculating, need to calculate the values of a and b. Well, using those 2 points to start with, we can just sub those in. So we can say -5, minus 25, a times -1 plus b times -1, take 24. If I can rearrange it and solve it a bit, I get a take b equals -1. So I'll call that equation 1. Now we know that the point -1, -25 is a stationary point. So we can say dy dx is equal to 0. If we find out what dy dx is, we get 2ax plus b. And at x equals -1, I get 2 times a times -1 plus b, which is just -2a plus b. I'll call that equation 2. Hang on. Yeah, it's a stationary point, so I can say that my derivative is equal to 0. This is what my derivative is, so I can just say -2a plus b is equal to 0. That's going to be my second equation. If I add equation 1 and equation 2, I'll have a plus -2a minus b plus b equals -1 plus 0. So I get -a equals -1, so a has to equal 1. And then put that back into, well, probably equation 1's easier. So if I do that, I get 1 take b equals -1. So if I solve that, b is going to be equal to 2. So there's my two solutions. B equals 2, a equals 1. The third part, part C, we've got the point 4 -1 is a stationary point on the curve y equals f of x, for which x is greater than 0. Given that our derivative of f of x is 1 over x, take 1 over 4, determine the nature of the stationary point. So determining whether it's a local minimum, maximum, or a stationary point of inflection. So we know that f dash of x is equal to 0 for a stationary point. So at what value do we get that? Well, 1 over x take 1 over 4 equals 0. We get 1 over x equals 1 over 4. So therefore x has to be equal to 4. And I can make a nature diagram. So we've got x, f dash of x, and our slope. Now I know my turning point or stationary point is at x equals 4. My derivative of that is 0, so the slope of that is flat. So now just picking points either side of 4, we'll go 3 and 5. So what happens for f dash at 3? I get 1 over 3, take 1 over 4. That's going to be 1 over 12. So it's positive, so I get a positive slope. So that's all I'm interested in. And similar for 5, 1 over 5, take 1 over 4. I get minus 1 over 20. Okay, we've got negative, so it's a negative slope. So from this, I can say it is the gradient changes from positive to 0 to negative. So the point 4 minus 1 is a maximum turning point. So looking at curve sketching. So to sketch the graph of any function, y equals f of x, we've got a few different points that we can go through now. The first one is obtain the y-intercept. So we find that by finding f of 0. We can also obtain the x-intercepts. So that's when we find f of x equals 0. Finding the x-intercepts sometimes can be complicated because there's more than one, but we know how to find them for a lot of different values. Third part is to calculate the x-coordinates of the stationary points by solving for when the derivative is equal to 0, and we use the equation of the curve to obtain the corresponding y values. The fourth option is identify nature. Of the stationary points, which is what we did in that last example there. And we've got a fifth example, or fifth point, calculate the coordinates of the endpoint. If we have a restricted domain. And any other key features where appropriate. So mostly we'll be looking at those ones there. So worked example 10, sketch the function y equals 1/2 x cubed, take 3x squared plus 6x, take 8. Locating any intercepts with the coordinate axes and any stationary points. Well, to start off with, it's usually easiest to find the y-intercept, and that's by making x equals 0. And if we do that, we get minus 8 for this one. And for the x-intercepts, same thing, but we make y equals 0. Oops, take 8. And if we solve that, We can do it by hand, and that's by using our remainder theorem and finding factors, or you can use your calculator. You can work that out as you please. I'm just going to jump straight into the solution. So we can find x take 4 is a factor. So we say x is equal to 4 is a factor. And we get x squared take 2x plus 4. And we have no way to factorize that, so there's only one x-intercept at 4. So the next thing to look at is stationary points, and that's by finding the derivative. So dy dx is going to be 3 on 2x squared, take 6x plus 6, and the stationary points when that is equal to 0. And if we solve that, we get x is equal to 2. And you can find that by using CAS or otherwise. Substitute that back into the function's equation. We get y is half times 2 cubed, take 3 times 2 squared plus 6 times 2, take 8. Work that out, we get minus 4. So the stationary point is at positive 2 minus 4. And using a sign diagram, so we have plus and minus. We know that 2, and we start positive, we get to 2, and then it is positive again. So the point 2 minus 4 is a stationary point of inflection. So what does that look like on a graph? We have an intercept at positive 4, a stationary point of inflection at 2, and we have a y-intercept at minus 8. So connecting the dots, or our key points, we get something that looks like that. So not very well drawn, but basic shape. So that's how we would sketch the graph. I'm going to leave the video here. In the next one, we're going to have a look at local and global max and minimum points. Thanks.